Any question or comments? Good afternoon.
Good afternoon, sir.
Good, thank you for replying. I'm glad that you're awake. How about the rest? Are you awake?
Yes, sir. Hello.
Excellent, very good. Okay, I believe we have only a few days left. I'm trying to finish chapter 13, only covering portion of it. I'm sure you have seen it before, but just as a review. And then next week, we have 2 lectures left, and I'm trying to go through a review process from chapter 2 all the way to chapter 13 by solving some problem. But please spend a few hours study, and then when we do the problem, please make sure that you have your calculator, your formula sheet, and pen and pencil, because the only way you learn that is that you do the problem on the paper, you see your mistake, and then learn, okay? And that's all I can do, okay? Let's start chapter 13. As we discussed last lecture, we are trying to define the view factor. I'm sure you have some idea what that means because we covered in building science, and we are going to review the 2 laws that we discussed. It was reciprocity law and also the summation law, because we are using these 2 principles trying to find what fraction of energy leaves one surface and will be captured by the other one, okay? That's very, very important in design of different type of system, because that's, you can minimize your energy by knowing exactly where energy has to go. The other one, we're trying to also find how we can calculate the net energy exchange between two surfaces. We start with the black surface, and then we go look at also gray surfaces. Again, this is an overview of what we have done in building science, just to remind you. As we mentioned as I mentioned last lecture, when we're discussing about view factor, depend which textbook you will see, you will find out different terminology. Some people call it view factor. The other one call it shape factor. They call it angle factor. They call it a configuration factor. Therefore, all of them more or less is the same thing, okay? It's only a geometrical factor. It identifies what percent of energy leaves one surface and will be captured by the other surface, okay? Therefore, trying to find the relation between the two surfaces. If this is perpendicular, therefore this surface will not see this surface. But if here, we can see portion of it. If you have this position, you can. We are trying to find the relationship, how we can calculate this view factor, okay? Therefore, you are familiar with this terminology called Fij, and Fij, it means what fraction of energy leaves surface I and will capture by surface B, okay? Surface I and surface G, okay? This is what energy leaves surface I, therefore this is the notation we use, notation of I. The first one is the surface energy leaving, and the notation 2J, it means that what will be captured by that surface, okay? This is where, again, remember mention fraction. Fraction is always between 0 and 1. If it's 0, it means no energy will receive by surface 2. Yeah, okay, look at, because it's particular, this surface cannot see this surface. And if it's 1, if actually 1 is encapped by the other one, we will see that one again. And please stop me whenever you have any question. If you look at here, this is two, let's say sphere 1 inside the other one. This is surface 1 and this is surface 2. The idea, as I mentioned, we mentioned shape factor of 1 to 2. 1 to 2, what energy leaves the surface 1 will be captured by 2. Then we can call it shape factor 2 to 1, what percentage of energy leaves surface 2 and received by surface 1. Therefore, we are trying to find this one and if you look at here, whatever energy leaves for surface 1 eventually will be captured by surface 2. Therefore, shape factor of 1 to 2 is equal 1, okay? Therefore, first, we're trying to understand the concept, visualization, and then we are trying to use the geometry to calculate that one. Now, we're trying to find this net energy exchange. Let's assume that we have two surfaces. Surface 1 inside here is the temperature T1, absorptivity 1, T epsilon. And surface 2, we assume is black surface. Therefore, we're trying, this is emissivity is equal to, therefore absorbability is equal 1, okay? Emissivity of 2 is equal 1, therefore emissivity is equal, absorbability is equal 1, okay? Let's write this equation that we have. Therefore, we can mention there's a continuous energy exchange. Therefore, we look at here, we're looking at this sort of a steady state scenario, equilibrium case, okay? Continuous energy exchange among the body as a result of reciprocity rule, okay? If you look at here, it's mentioned is continuous exchange. Therefore, this is going on and on until reach equilibrium. Okay. Therefore, that's the scenario that we're looking. Therefore, we look at case number 1 to see how we can solve this problem. Okay. Therefore, now we have two surfaces. Surface 1 in the middle one. Remember, middle one, and surface 2 is the exterior one. Okay. Therefore, 1 here, 2 here. I can easily write a set of equations. I mentioned amount of energy leaves surface 2, and we mentioned that we mentioned black body is equal to sigma T to power 4. Okay, this is the amount of energy because this is black surface, the emissivity is equal 1. Okay, and then we mentioned energy is absorbed by surface 1. Therefore, this energy leaves surface 1. But only portion of that will be absorbed by surface 1 because it's not a black body, okay? Again, if you would like to go back and look at here, it leaves all the energy here. We can calculate because we know the temperature and assume it's black body. and portion of that will be absorbed by this surface here, okay, because this is not black body. That's exactly what we're trying to say here, okay. And then we mentioned again energy radiated by a small surface, the one at the center. This amount energy, this because it's not black body, is emissivity, has a certain emissivity. We write it down and we calculate that one. And then we can say the net energy exchange for surface one, okay. This one was absorbed. This one was radiated back, emitted back here, emissivity. Therefore, I can write this equation, net energy between these two, net energy absorbed by surface one is equal, this is absorbed and this emitted. Look at here, this energy emitted by surface two, portion was absorbed and then emitted back here, that way, okay? Now, if we assume the case that you have alpha, we've used before last lecture, we mentioned absorbability and emissivity are the same. Therefore, we can say the net energy exchange, the surface is equal to this one, okay? You can calculate the net energy exchange between the surface emissivity of one and that, okay? This is one case that we look at it. Therefore, now we can see, we can calculate the emissivity between the black body and gray body, and this is energy exchange between these two surfaces, okay? Now let's look at the second scenario. Second scenario that you have seen it in your building science, look at here, parallel plans of infinite extent. Why, who cares about this statement here? Why we are saying infinite extent? What it help us to justify this extent? What do you understand about this statement here? Can somebody help me?
Can you say it again, sir?
What that means, we mentioned infinite extent, why he or I have to emphasize in this part? How this can help me?
There's no loss like from the end of
Excellent.
the end of the plane.
Excellent. Therefore, these two parallel plates are parallel, long time length. Therefore, the energy loss from the end part, this energy, as mentioned, we are assuming it's diffuse. Okay, diffuse, it means portion comes here and portion will escape here. Therefore, this is long. Therefore, the amount we can assume the portion escape from here, we can ignore it. Okay, let's look at this scenario. We have two parallel plates. There are two different characteristics. Temperature 1, emissivity 1. Temperature 2, emissivity 2. Therefore, let's assume a certain amount of energy emitted by this surface. The temperature is T1, emissivity is E1. Therefore, this is the amount of energy emitted from this surface. Will hit this surface. Portion of them will be absorbed. And portion, we can say alpha, this one. Okay, this will be absorbed, and the rest will be come back. Okay. A portion will be absorbed and the rest will come back here. We'll hit this surface again. A portion will be absorbed and the rest will be emitted back. Look at here, I'm saying emitted back. I don't care about reflectivity. I'm only looking at emission. Therefore, since these two plates are parallel and have a long length, this process will go back and forth, okay? Therefore, I can go back and try to find out how much energy emitted from this surface, how much energy absorbed here. I can write this equation. Therefore, I can write energy loss from plane 1. Okay, plane 1 is this one. Okay, again, come back here. This is plane 1. Energy loss from this plane 1. This plus next one and so on. Therefore, look at here, emit, portion will be absorbed, and the other portion will be emitted back. Hits here, absorb, and the portion will come back, okay? Therefore, we write the net energy loss from plane 1. This is the first one, this is the second part, and this will continue long, okay? Because we mentioned this is parallel plate and it's a long plate, okay? I can write energy gain from 1. Therefore, this is loss from plane 1 and energy. There are some energy gain from plane because the temperature that plane 2 is at T2. Therefore, this continue. Therefore, I can calculate the net energy with exchange between 1 and 2. If this, I add them together, if you don't remember, go building science, and you can see it here, this can write this geometric function. Therefore, we can easily mention this is the net energy exchange and times this term here. And this we call it effective emissivity of between surface 1 and 2. Now, if I have two surfaces and none of them are black, I can look at the effective emissivity of these two, okay? And this is the effective emissivity, you have seen it before. Look at here, we're talking about effective emissivity of surface 1 and surface 2. This we can calculate the net effective emissivity of it. Now we have equation that we can calculate the net energy exchange when the surface are not black, if they are gray. And that's gray, it means they have certain emissivity. You can take into consideration of this effectiveness, okay? Therefore this one. Therefore now we are able to calculate how much energy emitted from one surface, Stephen Boltzmann equation, and we calculate if you have two surfaces, if they are seeing each other all the time, we can calculate if they are not black. Now I would like to go to the next part and look at the percentage. As I mentioned here, is look at here, read this statement and trying to understand why we are saying FSR, or we call it Fij. Look at here, the first part you mentioned fraction radiation. If you do any calculation and you find your share factor is 6, I'm sorry, you're wrong, because it's between 0 and 1. Fraction, because we assume the total is 1, only fraction I will receive. Leaving a diffuse surface. Why we are mentioning diffuse surface? Why diffuse surface?
All directions.
Uniformly all direction. Therefore, when leaves that surface in all direction, the same magnitude. Okay, therefore there are the two we have to keep in mind when we're defining shear factor. The first one here is fraction. The second one, we assume the surface is diffuse and then passes through a non-participating medium. Why do you care about saying this term?
It's not going to absorb anything.
Excellent. Therefore, the air, whatever the gas between these two plates will not absorb any radiation. Therefore, leaves one surface and receive by other surface. Therefore, if you cannot probably apply this equation when you're designing a furnace, because in the furnace there's a lot of smoke. Therefore, some of those energy will be absorbed by this gas. Therefore, all the energy leaves here will not receive here, portion of it. Therefore, keep in mind there are some sort of element that we have to consider when we're trying to solve the problem. Now, therefore, here is mentioned sender and receiver. Surface, this one at the temperature TS, AS, TR, and FR. Therefore, this is only depend how the geometry of between these two surfaces. Let's go and try to do that. Let's look at here is the first law, and it is called reciprocity law. Assume again, look at these two, this one, the two surfaces I mentioned, and I use 1 and 2 rather than a sender and receiver, because here, first we assumed in order to make it easy for us, there's no need to make that assumption, but in order to make it easy, I assume these two surfaces are black, okay? Therefore, energy emitted from the first surface. It has a certain area, but therefore this is watt per square meter times area. This is the watt energy leaves. Surface 1 to the direction of surface 2. Leave surface 1, reach surface 2. Then I will write for the second one. I assume the second surface also is black, but it just makes the problem easier to explain, okay? Again, this amount of watt per minute per square meter times the area of the surface 2. This tells me how much watt leaves the surface 2. How much leave and what portion received by surface 1, okay? Now I can easily calculate the net energy exchange between two surfaces. Surface 1 and 2. This amount leaves surface 1 area, this one, received by surface 2, and some energy leaves surface 2 and reach surface 1. Therefore, I can calculate easily the net energy exchange between these two surfaces. If I know the temperature here, I can do that. Now, let's look at the principle. If I assume the T1 is equal to T2, what that means? It means this one is equal to this one, because this one is sigma T1 to power 4. This one is sigma T2 to power 4. If the temperature are the same, therefore these two are the same, right? Now I go back and replace in that equation and mention this is then, if I assume this one, there is no energy because both of them are the same temperature. Therefore, when they are the same temperature, they don't have any exchange, okay? If I write it down, this term become here is AB2, this 2 minus this one. Okay, this is the same equation here, but this one and this one is equal. I take it out of the bracket and I put it here. And since temperature of T1 is equal to temperature of T2, the net energy is equal to 0. Am I correct?
Yes.
Fantastic. Thank you, sir. You are still awake. Now, therefore, now look at here. This term times this term has to be equal to 0. This term times this term has to be equal to 0. But the temperature here is 6,000 degrees. This term, it is not 0. Am I correct? Therefore, this temperature cannot be 0 because this is an energy emitted and has a certain temperature. Therefore, there is no 0. Therefore, this term has to be 0. When I multiply by this term, it becomes 0. Therefore, that's come to here, this conclusion. Because this has to be equal to 0. When it's the only time this can be 0, that this term be equal to this term. Okay? Therefore, please keep in mind, mention shape factor of 1 to 2 times area of the 1 has to be the shape factor of the 2 to 1, the area of the 2. This we call it reciprocity law. Right? Okay. Therefore, this is principle that we can use it in many cases because it's sometimes it is difficult, for example, to find shape factor of 1 to 2, but it's easy to find shape factor 2 to 1. I will show you some example. Okay, this is very easy to calculate. Therefore, when I have this one, I can use this principle here. I have this principle I have here to calculate 1 to 2. Okay, let me go again. If you look at here, this it will mention here. It's very difficult to calculate shape factor of 2 to 1. But I know from the principle, from the physics of the problem, shape factor, whatever energy emit from surface 1, it eventually reaches surface 2. Therefore, I can say all the energy leaves from surface 1 reach surface 2. Then I can go use back the reciprocity rule to calculate 2 to 1. Because I know the surface area of here, I know the surface area of here, I can easily calculate. This is one example. Because this principles mentioned whatever energy here will eventually be captured by surface 2. Therefore, I can go back and calculate shape factor of 2 to 1. Otherwise, it's very difficult to calculate 2 to 1, okay? And also, we have to keep in mind, when we are talking about shape factor, we have to also understand the physics of it, that look at here. We are saying energy emitted from surface 1. When the surface 1 is flat, nothing will be absorbed by itself. Therefore, here is shape factor 1 to 1 is equal to 0. If you have a convex surface here and look at outside, whatever energy leaves again here will not be captured by surface 2. But in this one, if we have concave, it's the other way. Some of the energy emitted here eventually will surface absorbed by surface 2, captured by surface 3, okay? Some energy leaves here, this will go out, but portion will be captured by surface 3. Therefore, again, we have to understand that we are assuming, as I mentioned in the previous slide, this is, we assume is diffuse. It means it emit in all direction uniformly, okay? Diffuse, they mention all directions. This is one assumption, and I assume here that the air here or the air here will not capture any of those things. Again, this will help us again in the future to be able to analyze some problem that we are dealing. Any question? Any question? Okay, then I'll go continue. Again, I put some statement here. Please look at radius because that will help you to be able to analyze the problem and understand the problem. First, again, I repeat the same thing, fractional radiation. Again, if you do a problem and you find shear factor is 65, it means wrong, okay? The second part, it mentioned the underlying assumption in this process that radiation on a surface received from a surface directly proportional to angle of the surface that in the surface, okay? Again, we are going to calculate those one here. This would be the case only if the radiation coming off this source is uniformly in all directions throughout its surface. Again, we assume it's diffusive, okay? And the medium between the surface does not absorb or emit or scatter. Therefore, the medium that does not absorb. The gas by itself does not have any temperature that emits surface and does not distract the scattering the radiation coming from that surface. Okay. Therefore, when you're trying this one applying to atmosphere, probably cannot be applied because in the atmosphere there's a lot of gases that absorb some of the radiation, and also because of the particulate in the atmosphere scatter them. Okay. That is, this is the case when the surface is isothermal and diffusive. Therefore, we assume even the surface, the temperature everywhere is the same, does not change along the length. Therefore, it's isothermal. The whole area is the same temperature and diffuse, okay? Again, these are something keep in mind that don't jump directly and trying to say I'm using this. You have to look at the problem, you have to look at the application and to see how many of this assumption is correct about your problem, okay? Yes, we have a equation, we can do that, but we are making 65,000 assumption here. You have to make sure that those assumptions correct to the problem that we are going to apply. Again, it measured geometrical, therefore a lot of work has been done. If you look at your table 13.1, we have, if you have two parallel plates, again, remember, again, this is something make mistake here, the parallel here is, these are parallel, is not enclosure. You have two plates parallel, a certain distance, you have two diskettes here, and parallel again to that. You have two plates, again, perpendicular that you have. You can use this equation when you're using it, for example, for simulation that you're changing, easily you can calculate. You don't have to go to graph every time. Therefore, this equation has been obtained. There are also this scenario that we have some equation. Therefore, based on all of this, you can see that this is the result of that equation that we had it before. Okay. Therefore, now we can use as a design for graph. But if you're doing some simulation modeling, you have some equation that give this graph. Again, pay attention to here. Here is this gave you shear factor of 1 to 2, 1 to 2 from this one to this one, depend on the distance that you have and the size of the plate that you have. Size of the plate that you have. This one A1, this one A2, okay? Therefore, this shows the relationship D over this. This one, again, look at here, it gave you L1 over D, and here it gave you shear factor of 1 to 2. And you notice here the shear factor is maximum 1 and plus 0, okay? And you have also for when you without perpendicular together, again, this comes to the size of the plate, L2, L1, and weight, okay? Therefore, this gave you again L2 over W. This is L2 over W. And here you can see is L1 over W. That gave you, okay? But again, the shear factor goes from 0 to maximum 1, okay? Therefore, these are gave you some easy graph that when you're designing, involved in such a thing, easily come and get this number. But if you're doing some simulation and they keep changing, you can use those equation was given in table 13.1. Yes, sir.
The area here has no effect on the graph, in this graph.
The area has been shown by the dimension of W and L2 and L1. Therefore, these are in the dictating the area.
Okay.
Here, L2, W, L1, and so on. Therefore, that dictates the dimension of the plate and so on.
Okay.
Indirectly represented, sir. Again, if you have two diskettes, the distance of L, again here, R1 and R2, okay? Therefore, you can see that this, again, the R here representing the area, R2 is the area, and L is the distance. Therefore, here again.
Sir?
Yes, sir.
Do they have to be non-equal, or can they be both R1 equal R2?
It could R1 be R2.
Okay, it doesn't matter. There's no size.
Now
needed.
here
Okay.
mentioned again, the only thing is mentioned if you use this graph, give a shear factor of 1 to 2.
Okay, from bottom to top.
Of bottom to top. And here, if you're considering this one, L over R1, if you're considering this one, 2 R over 2. Therefore, you have to make sure that that's why I mentioned 1 to 2. Here, this is you are referring to surface 1 here, okay? And this part has to be surface 1, okay? Because R1 is surface 1 here.
What if we want from 2 to 1
Excellent.
with reciprocity?
Excellent, sir. Excellent.
Right.
Yes, you use 1 to 2 from here. Then you go reciprocity rule and calculate.
Okay.
That's
Depending
good.
on the area. Okay, thank you.
Sure. Again, when you have two pipes here inside each other, again, show you R1, R2. Therefore, they solve those equations that as I mentioned, all pure geometrical. They did it and plotted in case that you're trying to apply it for the case of design. Okay. Therefore, but there are a lot other cases that they have done it and they plot them, and also again it's geometrical. For example, if I'm sitting in a room and trying to design for window, they're trying to find if I'm sitting inside the room and window it comes, what portion of energy comes to me. Again, they have done this work, and you can find it even in when they study thermal comfort. Okay. And therefore, all of this geometrical work has been done, and there are some equations to calculate for every almost possible scenario. Therefore, in the future, if you're dealing with such a scenario, I'm sure that you can find a graph or equation to give you shear factor. Okay. Now, this is where we look at again to summarize that reciprocity relationship. As I mentioned again, this is the equation that we have. A or I. Shear factor of I to J is equal J to I. This is reciprocity rule. Again, please, remember, this is reciprocity rule. And keep in mind, this. It has to be multiplied by the area. The only time we can say these two is equal when the area are the same. This is a common mistake ladies and gentlemen are made. This is not equal if the area are not equal. Okay, therefore I know this sometimes they write in the equation and they mention this is, then it eventually they make decision this is equal this. The only time this two shear factor of J to I is equal I to J if the area is the same. Therefore this and this be cancelled. Therefore be careful trying to understand the physics of it and then apply the equation that later on. Okay, then go to the next one. If you're sitting inside a room, or if your energy comes from a window, okay, and the window, if we're looking at enclosure, again, please understand what the meaning of enclosure. It means they cannot escape to go out. Therefore, if I'm inside a room and the door is closed, and I'm dealing with four walls and the ceiling and the floor, whatever energy emitted from my body will eventually be captured by these surfaces. Therefore, the summation rule mentioned here is shear factor here to this surface, to this surface, to this surface, the summation of all. It means what that means, shear factor, it means the energy emitted from this point, portion will be absorbed here, portion will be absorbed here, portion will be absorbed here, and if you add them up, all of them eventually will be absorbed by the surface of the wall. Therefore, this is the meaning of this one. Shear factor from surface I to J, and J is going all these surfaces is equal 1. Again, the meaning here is whatever energy emitted from this surface eventually we capture this one. Again, this equation, please remember, apply to enclosure. It means confined space. The sum of view factor from surface I to an enclosure to all the surface of the enclosure, including itself, must be equal to 0. Okay? The simplest one, look at yourself sitting inside the room right now. Your body emits some energy around 65, 70, and all of them, if the door is close, all of them will be captured by the surface of the wall, ceiling, walls, and floor and so on. That's the meaning. Again, remember, this is applicable when you have enclosure. Sometimes they mistake, some students, they use it for open space. Therefore, that's the physical meaning, okay? Now, again, another rule, we call it symmetry. Symmetry, it means if you have a surface like this, 1, 2, and 3, and if 2 and 3 are equal size and similar, you can measure shear factor from 1 to 2 is equal to 1 to 3. Again, this is symmetry, okay? 1 to 2 is equal to, again, this is symmetry that you can apply. This sometimes help us, again, for sophisticated equipment to geometry to make it simple, okay? Therefore, now we have reciprocity rule, we have summation law, and we have symmetry rule, okay, or law, okay? Therefore, this is that can help us to make easy for some geometry to calculate the shear factor, okay? Any question? You don't have any question? I do have a question. I'm sure you remember this one. Can you do it now? Therefore, assume that this is geometry that you have. Again, this mentioned about architect. Assume that you're going passing algorithm and trying the guy, architect trying to evaluate the percentage of the light through a store window A1. This is the window. Here is opaque wall. Here is opaque wall. And here they would like to see what percentage of energy or light, daylighting, goes from this one will come here. What percentage of light goes through window A1 will be eventually end up here, okay? Let's at this moment forget about the size, Let's assume the general 1, 2, 3, 4. I'm trying to calculate the shear factor of 1 to 4. Could you please try? Are you trying?
Yes, sir.
Please do that. A good exercise and find out what is your mistakes here. Again, to solve this problem, keep in mind that you had this graph, okay? You have this graph. Assume that you can calculate shear factor of 1 to 2 from here. The only time you can do it when these two planes cross each other, okay? Therefore, I can use this one because this plate A2 and A1 are connected together. Therefore, assume that you can calculate A1 to 2 here, okay? But in our case, we are trying to calculate a scenario that they are not connected together, okay? Here, look at A1 and A4, they are not connected, but you can use that graph to calculate 2 to 3 or 3 to 2. You can calculate this one, I call it 5 to 3, but you cannot do it directly 1 to 4. Therefore, sit down and try and take your time because this is almost the end of our lecture. I'm not going further than this one. Trying to do it, and if you have any question, let's ask and discuss it. Our lecture will finish by shape factor, okay? Therefore, this is an overview that we had in building science, okay? I cannot hear anybody. Was there any question?
The height of A2 equal to 2?
Say it again, please.
Is the height of A2 is equal to 2?
Don't worry about this, the height at this moment. Just write it down in general term.
Okay.
Okay, assume that we don't have the dimension. I'll give you the dimension later on. But at this moment, I would like you apply the concept, okay? Okay, let's start together. Again, please draw this on your paper that as we go and slowly to remember what exactly. Again, to simplify it here is we have surface 1, we have surface 2, we have surface 3, we have surface 4. To make it easy, I call A plus 2, 5, A plus 2, 5, and 3 plus 4, 6. Therefore, this, the total of this plate, I call it 6. Rather than writing 3 plus 4, I mentioned 6. Okay, just trying to write the notation, that's all. Again, also remember, I can calculate a shape factor of 5 to 6. I mentioned shape factor of 5, F5, 6 times A5 is equal shape factor of 6, F6, 5 times A5, okay? Or I can mention shape factor of this to whole plate of 6 is equal shape factor of this to this, 1 to 3, 1 to 4, 2 to 3, and 2 to the 4. Therefore, I can write that as expression. Okay, please plot this graph here, this drawing, and that we go step by step that we can remember what we mentioned, okay? Okay, let's go back and continue. I write it down, mention as I mentioned, I can mention surface 1 and 2 represented by 5, 3 by 4 represented by 6. If you look at the drawing that you have, you can write shape factor of 5 to 6. I can break it down, mention 2 to 3, 2 to 4, 1 to 3, and 1 to 4. Please go through this expression. If you have any question, let me know. Just until here. Okay? Make sure that you really understand. If you have any question, please do ask me. Remember what we're trying to calculate? We are trying to calculate this one here. Look at your graph that you have. I believe we can calculate 2 to 3 because 2 and 3 are connected. If I don't know the dimension of here and the dimension of here, I can calculate, okay? So I can calculate 2 to 3, but I cannot calculate 1 to 3 because I do 1 is this one and 3 are not connected together, okay? I cannot calculate 2 to 4 because 2 is not directly connected to 4. 2 is connected to this one. Therefore, I go back and try to write some other expression that I can calculate, okay? For example, I can write 5. I can write again this expression 5. 5 is summation of 1 to 2 to 3. I can write this one. Assume this my system is here. This one, 5 and 3. I can write this one. I can calculate this one from the graph that I have because they are 5 and 3 are linked together. Okay, I can write 5 to 3. 5 to 3, it means 1 to 3, 2 to 3. I can calculate 5 to 3 directly from the graph. I can calculate 2 to 3 from the graph and then subtract them to find 1 to 3. The same thing, please interrupt me whenever you have a question. I can calculate. Yes, sir.
Area 1 is a window. Area 2 is opaque.
Oh,
So they have
the only thing I mentioned opaque at this moment here is just there are 2 different surfaces. Okay, there are two different surfaces. That's all I'm taking. Assume here is also window. I care less because at this moment we are only looking at the geometry part. Okay, I'm trying to mention the characteristic of surface 1 and 2 are different. Okay, that's all I'm trying to say. Therefore, I wrote 1 from 5 to 6, the expression that you wrote. Then I can say here, if I go back, I 1 to 3, I cannot calculate because they are not connected together. I cannot use that graph. But I can write one more expression. I mentioned 5 to 3. Shape factor of 5 to 3 is equal F5 to 3 times area 5 equal area 1, shape factor 1 to 3 plus area of 2 times shape factor 2 to 3. That's exactly we wrote here. Therefore here, if you look at here, this is you can calculate. Please pay attention. This is I can take it from the graph I have. This one I can calculate from the graph I have because 2 and 3 are connected. But 2 and 4 is not known. 1 and 3 are not connected, and 1 and 4 here. Therefore, I have this. I'm looking for the only one I know on this one. Okay, this one and this one. Then I can go write another expression for only surface 5 and 3. I ignore 4. Okay, I ignore 4. If you look at the graph, the picture that you have, 5 to 3, I can break it down and mention 2 to 3 plus 1 to 3. Okay, but if you look at, I can calculate this one from the graph. I can calculate this one from the graph again. Therefore, I can go and substitute in this expression data here, these two terms. Then I can go back again and write another one for figure 2 for this one here and 6. This one, A2 to 6, I ignore here. I just say my system is this one and this one. Again, I 6 and 2. Therefore, become 4 to 2 and 3 to 2. This one, again, I can obtain from the graph. And I can calculate for 2 and 6 because I have the dimension of 2 and dimension of 6. I can do it again, the graph. Therefore, please pay attention here. I can write down 2 to 6 is equal 2 to 3 plus 2 to 4. Again, remember when you're writing reciprocity rule, you have to put all those areas. Now I can go back to this equation here and replace this one right here from this, because this one I can obtain from the graph. I can obtain this one from the graph. Therefore, if I put back in this equation that I have, I can find the shape factor of 1 to 4. Because this from here to 3 is come from here, 2 to 4, and 1 to 3. For all of them can be obtained from this 3 expression and put in this expression form. Again, remember, this is A1 to 4 times A1 equal this one. Look at it, write it down, and please try to understand. Please try to understand. If you have any question, please do ask me. Don't be shy, please ask.
Can we get the numbers now?
Why do you care about the number? You can put any number, you can go and solve it. The whole idea here is to understand the concept. Assume 2 meters, 3 meters, 5 meters, something. That's why I didn't put the number, because I don't want to be sort of focused on the number, trying to understand the concept that we can apply it. And put any number and try to go on to calculate. Just put 2 meters, 4 meters, 6 meters, 10 meters, doesn't matter. Do you really understand the concept? Do you need more explanation? Please ask me. Finish?
Yep.
Okay, therefore now we have a shape factor. Therefore we can go and calculate the net energy exchange between two surfaces. And the energy here is simply, you can apply here is shape factor of this one between surface 1 and 2. And you have n surface, the only thing you have to take care of the shape factor for each one. Okay, you can calculate the shape factor for this one. Therefore now we can take in consideration the two bodies are not seeing each other all the time, and there's a portion of energy leaves surface 1, reach surface 2. Okay, for that we can do that. Any question, please? Is it clear to you?
Do you mind going back to the last question just for a second?
Yes, dear. Take your time and try to understand, because this is not, you have to only understand the methodology.
So I might have made a mistake in writing down the questions, but I had.
Yes?
Sorry, 1 second. Does the area 2F2 to 3 not end up canceling out?
2 to 3, why should we cancel out?
Like in the equations?
Because that's
Oh
why.
no, I'm sorry, I found it. Never mind, sorry. Thank you.
No problem. Okay. Therefore, you can calculate some of them. In this case, you can, if you know the area of the 5 and 6, you can go and use the figure, calculate shape factor of 5 to 6. If you know the area, that's the dimension of 2 and 3, you can go and calculate from the figure, and also the rest. Because if you go back to this equation, you can see that this one, you have all the information. Area 5 to 6 can be obtained directly from the graph. 2 to 6 can be calculated directly from the graph. 5 to 3 can be calculated from the graph, and 2 to 3 we can calculate. Therefore, all of this known value, because if you know the dimension, you can calculate this one from the figure, this one from this one, and this one, and put in this equation. Okay.
Yes, makes sense. Thank you, sir.
No problem there. Let me go to see if you have any question for me or not. If not, let's look at here. A truncated cone has top and end diameter of 10 centimeter and 20 centimeter, and a height of 10. Calculate the shape factor between the top surface and the side surface. Remember the figure that you have. Again, let me go back. I'm sorry, what did I do? Look at this figure that you have here. from this figure that you have, or was it here, this one, you can calculate 2 to 1 or 1 to 2. But the problem, we are not interested 1 to 2, 2 to 1. We are interested to calculate where I was, my friend. Oh, yeah, I was interested to calculate this one. Shift factor between the top surface 2 and the side 2 to 3. Can you do that, please? While I go and get a glass of water. Any question? Therefore, these are the size given, okay? You have dimension, the diameter here, and you know the distance between 1 and 2. But the problem is not asking to calculate 1 to 2, therefore you cannot use the figure directly. It's asking to calculate the shift factor of top F2 to 3. What percentage of energy leaves surface 2 will be captured by the sides?
Can we say that the total should be 1?
Yeah, we can say the total.
From 2 to 1 and from 2 to 3?
Yes.
The total will be 1. And
Yes.
from 1 to 2 to 1 to 3 equal 1. And we can, from the graph, we can get from 1 to 2.
And then?
Enough.
I do not know, really.
If we have the percentage going from 2 to 1, and that the total should be 1, we subtract from 1 the percentage from 2 to 1, it should give us from 2 to 3, right?
Yep, let's see if you're correct, sir. Okay, let's go. You're right. Therefore, it's shift factor of 2 to 1, 2 to 2, and 2 to 3 has to be equal 1. That's all I'm saying here is shift factor of 2 to 3, 2 to 1, and 2 to 2 is equal. You know, the 2 is a flat, cannot see itself, therefore this equals 0. Do you agree?
Yes, sir.
Therefore, now we have to calculate shape factor of 2 to 3. And that's if you have used this equation at the top, become 1 minus this. Therefore, now you can go back and calculate shape factor of 2 to 1. And you have the reciprocity rule. And you can calculate this one from the figure because you have the dimension. Again, the shape factor, if you look at the figure, what we are playing with this one here, because it gave you from 1 to 2. If you remember that figure, that's why we are playing with this expression here, not just because of the sake of expression here. You can look at here. What was it? This one. This gave you shape factor of 1 to 2 from here to here. But your application, you need 2 to 1. Therefore, that's why we wrote reciprocity rule. Okay, keep in mind here, give you 1 to 2. Therefore, we come here and we do this one. Therefore, from figure 1, you have this dimension, the distance, the diameter of the 1, the distance, diameter 2, and you from there, if you use your textbook to see if you can get the shape same value, shape factor become 0.12. If you have your textbook, please open it and try to see if you get the same number or not. I want to make sure that you do not make any mistake in future. Now you have shape factor of 1 to 2, and you go back, and here we don't have any area because this has been written a summation rule, okay, summation rule. Now, but here you have 1 to 2, but you need 2 to 1, 2 to 1. Therefore, you go back and use reciprocity rule here. You have 1 to 2, you know the area of 1, you know area of 2, you calculate 2 to 1 and replace it here. And look here, this is exactly what we did here, okay? We use this equation, reciprocity rule, to calculate 2 to 1 because we know 1 to 2, and these are the area. Pi and pi has been cancelled, and these are the diameter. It doesn't matter because divided, and 2 because it's pi r2. Okay, this 2 is over there. The shape factor of 2 to 1 is 0.48, and you go back and replace it in this equation that you have, and you can find the shape factor of 2 to 3 is become 0.52. Any question? Go step by step. Please, if you have any question, ask me now because we are not coming back to this chapter anymore, okay? Because we have 2 lectures, we have go back and chapter 2, 3, 4, 5, 6, 7, and so on to that.
For the equation you used L over R1 and then L over R2. Maybe it changed in the additions, but I'm pretty sure for the most recent addition, you have to use R2 over L for the second equation, which would lead to a different shape factor 1 to 2.
Let me go back because let me just look at here what you're saying. You're mentioning to this one, right? This one?
Yeah.
Yeah, so it says to use R2 over L.
Mention R2, this one?
No, the lines are R2 over L, not L over R2. The lines, not the x-axis, the lines.
If you follow the lowest pink line, it'll say R2 over L is equal to 0.3.
This one?
Yeah, whereas we calculated L over R2, which I believe was incorrect.
This one, right? You're talking about this one, right? This R2.
Yeah.
Yes.
Okay, let me check. Let me go back. Here we're talking about this one. Okay. The number that we have is okay. Let me just go back. The diameter is
10.
It's 10 over 10, so it's the same.
Okay, 10, 10, and 10, okay. Let me write it down because my memory here says 2, or 2 is
It becomes 10 over 10, so it's 1.
10, and R1 is become 20, and L is 10, okay? What you're saying here is L1, the figure mentioned R over L, right?
So the second check mark should be R2 over L, which would be 10 over 10, I believe.
Then R1 is the same?
No, R1 is 20.
I mean, this R is 10.
R1 isn't R1 20?
Yeah,
Says
R1 is also
10
20, I didn't notice.
10 for R2 and 20 for
Anyway.
R1.
Okay, please again follow and check it because I have to go back and look at the textbook again. This figure that you're saying, is it correct or not? The figure that it mentioned is correct, right? The only you're talking about the solution, right?
Yes, the solution is wrong.
Okay.
We think it's wrong.
You're-
If not, it's
I'm
the
not-
diagram that's
I'm not
wrong.
going to argue, but again, as long as you follow that diagram,
Yeah.
that's fine. Okay, let me do one more problem. Therefore, the rest of those are you're sitting quiet, the discussion about this part. Please check with the figure 13.7, and the question was that we are not using the correct number here. Okay, that's the discussion. Okay, I will check it again, let you know next lecture. Again, let me do one more problem. The question now here is mentioned, this was half of the problem. While you are working, then I can go back and check. The asking here, it was the problem, it's one part left, and the part left, it mentioned, and the shift factor between the side and itself. It's trying to calculate the shift factor of F3 to 3. F3 to 3. Please do that while I'm doing my work assignment. Trying to calculate the shift factor of 3 to 3.
Sir,
Yes, sir.
I think that it was correct because it's R over L and the radius is 5, so it's 5 over 10.
Yes, I realize it. You're right. Thank you. People, they would like to give me a hard time. 2 equal 20, become Or 2, it was 10. Yes. No, I believe it was the notation that's giving this one. Okay. The answer
Yeah,
is
my bad. I used diameter instead of radius. My bad.
okay. This one is L over R1, and this one is R over L2. Yeah. Happy ending. Therefore, now we have this one. My mistake is correct now. By default is correct. Now we are going to have to go back and calculate F3 to 3. How can we do that one? Any suggestion? Now it's asking also shape factor between the side and itself. F3 to 3. Any idea?
We have F2 to 3 and F3 to 2 should be equal. And then we have F3 to 2 plus F3 to 1 plus F3 to 3 equals to 1. So then we can find
We do not know F3 to 2. We do not know F3 to 1. And we do not know F3 to 3. If I write the summation rule, it mentions F3 to 1 plus F3 to 2 plus F3 to 3 is equal 1.
yes.
I do not know 1 to 3. I do not know 2 to 3. I do
But
not.
what we can know 1 to 3 by doing 1 to 2 plus 1 to 3 equals to 1.
I do not know. So write it down.
Okay.
Summation rule mentioned F3 to 1 plus F3 to 2 plus F3 to 3 is equal 1. I do not know F3 to 1. There's no way to calculate because I don't have the graph for it. F3 to 2, I cannot calculate because there's no graph. F3 after, therefore the 3 of them is unknown. Now we have to use another concept to see if we can use that concept. Any suggestion? We calculate 1 to 2, so what? But here you're saying 3 to 3. And if you look at the 3, if I write the summation rule for 3 to 1, I do not know. 3 to 2, I do not know. 3 to 3, I do not know. Summation.
Sir,
Yes, sir.
do we have reciprocity from F2 to 3 to 3 to 2?
Yes, we can do that. What can we do? I do not know 2 to 3 and I do not know 3 to 2.
Didn't we just calculate it 2 to 3?
No, I just calculated 1 to 2. That's all I calculated here.
Oh, well, 2 to 3. Yeah, exactly. I thought we already had that number.
Well, what can I do with that one?
Well, then now if we have reciprocity between 3 to 2 also, so we know that F3 to 2 is 0.52,
Okay.
and then we can try to find F3 to 1 the same way we did to find F2 to 3.
Yeah.
And then F3 to 3 plus F3 to 1 plus F3 to 2 is 1.
Okay, let's see if we can how far we can. Therefore, here we can write the reciprocity rule. As I mentioned, I do not know this one. I do not know this one. I do not know this one. Therefore, we have 1 equation and 3 unknown. But you mentioned that we can use reciprocity rule to calculate 3 to 2. But also we know that this one, shape factor 1 to 1, 1 to 2, and so on. This one is 0. Okay. Therefore, here they give us some idea how we can calculate this one probably. Yeah, we can calculate reciprocity for this one, but we have to go back. But also we know this one, the case, F1 to 3 is equal 1 minus 2. We already calculated this one. Remember, we calculated this one. Therefore, I can calculate 1 to 3 right here. And also I know 2 to 3, therefore I can now start to use reciprocity rule to calculate the other one. I can use reciprocity rule to calculate 3 to 1 here. From this expression we wrote for surface 1, we were able to calculate 1 to 3. This one we did a calculation before. If you don't remember, here, this one right here. Okay. Therefore, we can come back and do this one. Reciprocity rule. We can calculate 3 to 1 because we know 1 to 3 and that. And for area we can calculate, there's no problem. Therefore, from here we can calculate 2 to 3 because this one we calculated the value inside. This is 1 to 3. Okay, this is just to pay attention to this one. I made mistake here. We know equation right here. This one 1, 1, 3 to 1. Okay. Therefore, this has to be 1 to 3, right? Okay. Just pay attention to this one. I made mistake here. Okay. And then from there, we also use the reciprocity rule to calculate 2 to 3. And then we put it the summation rule and calculate. I made mistake here. Please pay attention to this equation that's here. Okay. Reciprocity here is A1, F1 to 3, A3, A2 to 1. Okay. Area 1 is circle, and here we can calculate area of 3, and this is the equation that we can calculate the area of 3, and we put it back here. This I made mistake here. Please pay attention. Okay, because A1 F1 3 A1 is equal to A3 F3 to 2. Okay, so use this equation, put the correct number here. You can calculate. Okay. Therefore, now we can use the summation, the combination of the summation rule and reciprocity rule to extract the information that we needed. Okay. Again, we use simply summation rule because we assume it's a confined space, and what energy leaves area of 3, it will be captured by 1, 2, and since it's a closed environment by 3 itself. Okay. We already calculated 1 to 2 before, okay? And also we can calculate the other one. So we can write another expression for surface 1, but here you can say 1 because it's flat, cannot see itself, the flat it cannot see, and there we have this expression. We already calculated this one right here, therefore 1 to 3 we can. And since we know 1 to 3, we can calculate 3 to 1 by considering reciprocity rule. Okay? With reciprocity, we can calculate it. And since we know 2 to 3 to 2, we can go back and calculate this one. Okay? Therefore, we can go back and calculate it. Please pay attention here. I made some mistake. I know I noticed I made a mistake. These two and these two, please pay attention because you're trying to calculate 3 to 2. I made mistake here. Please pay attention to this two expression. Okay. Probably the number is correct, but the notation here is not correct. Okay. Please pay attention to these two. And then we calculate 3 to 1. We can calculate 1 to 3. And also here, we can put in this equation 3 to 1 and 3 to 2 and calculate this one. Please pay attention to this expression. I just noticed these two. I did not put them correctly. Okay. Okay, because this is 3. How this? Yeah. Okay. Because you calculated 1 to 3. Okay. Therefore, this has to be 1 to 3. This is. Please pay attention to these two equations. Okay. Therefore, now you can see we can apply this rule, as I mentioned, is only to help us trying to calculate those shape factor that is difficult to calculate that simply. But now we see by applying these two law, again, reciprocity one and summation law, we can calculate. Again, please pay attention to these two equations. You apply it here to see if it, again, this is reciprocity rule we apply here, and this is reciprocity rule here. Make sure that here, I made mistake, please do not here, because we are trying to calculate 3 to 2, but I made mistake here. And also we're trying to calculate 3 to 1, I made mistake here.
Sir?
Yes, dear.
Are the numbers correct at least?
I believe the number, again, this is something that's a good exercise for you to do that, sir. I will not answer yes or no. Just the procedure here is correct. But these two, I made mistake here. Again, put the number to see if it's correct or not, sir.
Yeah.
Okay. Okay, therefore I will stop here because we don't have really time to go further chapter 13, and I don't want to just cover the material that we don't have time to practice. Therefore, this information is just a repetition that you have it in your building science. I'm not going to come back to chapter 13, but I will next week. We have 2 lectures left, and I'm trying to go through those material that we had it before. Chapter 2, 3, 4, 5, 6, 7, 9, and so on. Okay, natural convection, forced convection, and other parts. Okay, but please read it, study, and when we do the problem, at least you'll be able to understand and try to answer to your question. Okay, otherwise I can send you to a solution that you can sit down and do it. But the idea here is to have some discussion to make sure that you really understand and you are able to analyze the problem. Okay, it's not memorization, my friend. Memorization does not work at all. You have to really understand the problem. But again, please make sure that you know the basic how to use your calculator. Because some of you made a lot of simple mistakes in your calculation. Trying to use them, trying to really get basic information. Sometimes you have the idea, you know the reciprocity rule, but somehow, again, they based on past 10, 15 years experience, you cancel this A from here. Do not rush. Go slowly. You have enough time to go to the problem step by step and make sure that your procedure is correct. Again, the summation rule does not have any area. Even look at here, summation rule. That means energy leaves from surface 1, 3 to 1, 3 to 2. And this is only applicable to enclosure. Please understand the meaning of enclosure, because we are going to deal with them in natural convection and we are dealing them with radiation. Enclosure, it means the space is closed. Radiation does not escape from that one. Circulation of the air will not escape from that one. Okay, therefore we have to understand here. And reciprocity rule apply is only when this is like this. The only time this F1 to 3 is equal to 3 to 1 is area is equal. These are the typical mistake I make. Okay, these are the typical. I have seen them for the past. God knows the students are making this mistake. Anyway, please go back and study. And I'm trying to come with some question. These again some question for just having some discussion. And the only time it's helpful if you study it before and if you ask me during the solution. Okay. Thank you again. I will be around for another 10-15 minutes. If you have any question, please do ask. And I believe you have
the final exam.
Final exam. What you would like to know?
How many questions will be?
I have no idea, sir. You see, look at here. I was a student like you. I will make it the night before the exam. I do not know, sir. The question is not the number. The question, I have to consider the time. I can give you 2 questions, 3 hours. I can give you 5 questions, 3 hours. The question, I have to make sure that you can do it in 2.5 hours. At least you have half an hour, so you can go back and review it, okay?
Okay.
Because it's not the question how much you do not know. I know that part, how much you do not know. The whole idea, not me and all the professors, trying to see how much you really understood. Therefore, we're trying to cover, to give you something that we did directly, indirectly, not the same problem, but the concept that you'll be able to do it, okay? Therefore, the number of questions, I have to find out some question that you make sure that you can do it in 22 hours, 20 minutes, 2 hours and a half, that at least you have half an hour, you can go back and review. And if you're done, you're excellent, you can do it in 2 hours, okay? But again, I have to do it first myself, if I can do it or not. Again, I'm not a good student, therefore it may more time for me to do it than you. Okay, ladies and gentlemen, have a nice evening. I believe you have one more tutorial left today. All the best. I will be around here. If you have any question, please do ask. But please, before I forget, I believe mentioned you can have 2 pages of equation. It means 4 sides. I believe is enough based on my experience for the past many years. Do you need more pages?
Question is the tables you studied, like table 13.7, or those tables we don't need to.
No, those table 7.1, 8.1, 9.1, whatever is in the table, I will provide you. Because it's given is easy, but those are given in the text. You have to understand it. Therefore, I don't want to give you a question out of the text. I want you to write it down that do not make mistake, okay? Whatever is in the table for the fin, for the graphs and so on, I will provide you if it's necessary. If it's necessary, I will provide you. The rest equation, you can manage it and compress in 4 pages, okay?
The tables which has the Nusselt number for cylinder and for
Everything,
vertical and
everything is within the table, I will provide you.
okay, because those are equations, but
That's why, as I mentioned, if it's in the table, I will provide you, sir.
okay, thank you very much.
If it's in the table, I will provide you, sir.
Thank you.
Because it's easy, therefore it's in the table, you have seen it, but in the text, I hesitated because I want you do it yourself to know what exactly it is. Okay, have a nice evening. Please study. Next Tuesday, we are going to review. Next Thursday, we are going to review, but the only time is helpful if you study hard. All the best.
Thank you.
9.1 is a table. It's not equations.
Say it again.
9.1.
Yeah, as I mentioned, whatever is in the table, sir.
Okay.
I'll
Okay.
just give you an example.
Okay.
What is given in the table, if it's necessary, I will provide you.
Okay. Thank you very much.
No problem.
Sir,
Yes, sir.
for the formula sheets, can they